In this project, first you'll see the I2C LCD display that shows the distance measured in millimeters. Then we can have a quick look at how I've gone about connecting the Uno board ultrasonic sensor using a breadboard. I've also put a ruler down so that we can see what the distance between the object and the ultrasonic sensor is. Let's move it up to just over 100 millimeters and see that the reading on the LCD screen has changed. So this is a pretty accurate way to measure distance using an ultrasonic sensor and an I2C LCD display. Okay, so let's have a look where we start in putting together an ultrasonic distance measuring project. First of all, what you'll need is an Arduino Uno R3 board, an I2C LCD display, an ultrasonic sensor, a couple of jumper wires, and then obviously the sketch that we'll need to compile to run the project. Let's have a quick look at the ultrasonic sensor. Important things to note here is the first pin here is VCC, so we'll need to ensure to put that onto 5-volt power source. Then we have the trigger and the echo pin. Obviously the trigger pin will be sending the pulse out, the echo pin will be receiving the pulse, and then the thought behind it is the time taken from when the pulse is sent until it's received. Using the speed of sound, you can do a calculation that will tell you how far that wave has traveled based on how long it took to return. And then the fourth pin, we've got a ground. So we need to ensure we connect that to ground, however you go about that. Is this the first time you're connecting an ultrasonic sensor to an Arduino project? Do you have any other ideas perhaps of what projects can be done using an ultrasonic sensor? Please do let me know in the comments below. I'd love to hear of other good ideas on how to use this ultrasonic sensor. Alright, let's have a look at how we go about connecting it. What I'm going to do is point out the important bits, and the obvious bits I'll leave up to you guys to figure out yourself. So as I mentioned before, we need a ground connection here. So you can go about connecting the ground however you see fit, using a breadboard or using multiple grounds on the Arduino Uno board. It doesn't really make a difference. Then you need to connect the VCC pin from your LCD display to 5-volt power source. And your VCC pin from your ultrasonic sensor also needs a 5-volt power source. Then your SDA pin from your I2C LCD display needs to go to pin A4, that's analog pin 4. SCL needs to go to analog pin 5. Now these can go to any analog pins in any order, but the way that I've written my sketch is to use these two pins. Okay, let's have a look at the trigger pin needs to be connected to digital pin 8, and the echo pin needs to be connected to digital pin 7. And that's basically all in terms of physical connectivity for this project to work. Let's get over to the screens and have a look at how we go about getting the sketch compiled. Okay, so now that we're over to the screens, let's look at the sketch that needs to be put together. First and foremost, to get the LCD display to work, you do actually need to download some libraries and install them or upload them into your software. So I can do another video on that if you guys are battling to get your LCD displays to work. So these first 3 lines here are basically calling up the various libraries and setting the parameters of the LCD display. Also note I have specified the hexidecimal address of the IC2 display in there because you can have multiple I2C displays in a project, and they will have different hexadecimal addresses, so you know which screen you need to output to. So if you can't find the hexadecimal address of your I2C display, you're going to have a problem in getting it to work. But let me know in the comments if you want me to go into more detail with regards to these libraries, where to get them and how to make them work. Alright, then what we're doing is we're defining echo pin, and we're saying it's going to be digital pin 7. So we're creating a variable called echo pin, and we're saying that echo pin is in fact digital pin 7. And then we're saying trigger pin is a variable, and trigger pin is digital pin 8. And then we're creating variables called long duration and distance. This we need to be able to do the distance equals speed over time calculation to identify distance. Okay, then what we're doing is we're declaring that trigger pin or digital pin 8 is an output, and echo pin, which is digital pin 7, is an input. And again, here are some more declarations with regards to the LCD display. All right. Then a basic overview of what we're doing here is we're switching off our trigger pin, so we're not sending a pulse. We're waiting a little bit, then we're sending a pulse for 10 milliseconds, and then we're switching off our trigger pin again. Then what we're doing is we're turning on our echo pin so that we can receive input, and basically the time taken, we're recording the time taken for that pulse to return from when it was sent. And once we have that time, we know what the speed of sound is, we know the time taken, and we can therefore work out distance. Distance equals the duration the wave took and the time. Now, the speed of sound is 1,235 kilometers per hour. If you work it back into milliseconds, it's about 340. But because the sound has to do a trip there and back, obviously we need to double that. And then also we got to factor in our 10 millisecond delay. So this calculation can be a little bit complicated. I will give you guys this whole sketch as is. And if you'd like me to take you through the calculation and the thought behind how all of this works, I'm happy to do that. I just wanted to do a quick short video on how to put the project together. And then finally at the bottom here, we are outputting the distance onto the LCD display in millimeters. And then what happens is it runs again. So I mean, this really will run in probably less than 100 milliseconds, less than a tenth of a second it will do this. So it really is virtually a live reading when you are moving your surface closer to the sensor or further away. You'll actually see the reading on the LCD display changing in real time. So I hope you guys find that interesting and useful. I definitely will put a link to the sketch down in the description so you guys can download that sketch. All you then need to do is follow the directions on how to physically connect the wires and the pins, and then copy and paste that sketch into your Arduino software, upload it to the board, and you should be good to go. If you do have any struggles, let me know. Let's have another quick look at how this works. What I'll do is move the surface to a 50 millimeter distance from the sensor, then 100 millimeters, then 150, and then 200, just to show you guys how it works and how accurate it is. Hope you enjoyed this. Please give us a thumbs up and a like, and be sure to subscribe to the channel. Thanks, guys. Cheers.